Hello, I'm Brana Specification, and I'm here to speak to you in my capacity as the chair of the OpenMP Language Committee. As you may have heard, we recently released the latest version of the OpenMP specification, version 6.0. In this talk, I will be covering some of the details of some of the features we've added, as well as an overview of the features across the overall that we've added. In addition, I will also cover some of the changes we've made to the way the specification is written and otherwise implemented. And those are important because they help shed some light on where we're going in the future. So OpenMP 6.0 includes many major new features, as a major release should. It was officially released just last week on November 14th. It reflects roughly 3 years of work since the release of OpenMP 5.2. In fact, we actually had begun working on some of the features that have been added prior to the release of 5.1 a year before the release of 5.2. There are 415 issues that were enacted in building the new specification. So we use GitHub to manage the specification document and GitHub issues to manage individual additions, voted on by the language committee and then enacted into the actual specification source. These changes cover quite a bit of content. So the complexity of the issues varies widely. Compared to previous versions, the issues have tended to be finer grained, and so that contributes to the number of issues being as large as it is. So we've added, as I mentioned already, many major new features, and I'm going to cover a couple of them in detail, including something we call free agent threads, and also transparent tasks. Many of the changes in 6.0 actually update the tasking model. Transparent tasks, in particular, enabled an additional significant change in that we have now cast target data as a task-generating construct, which allowed us to support an asynchronous version of target data through the use of the no wait clause on that construct. The transparent task feature actually enables several other feature extensions that I might mention as we go over that feature. Another big feature that we've added is support for induction, and including support for user-defined induction. Induction is in some ways similar to something that's been in OpenMP since the very beginning, which is reduction operations. Induction allows you to, similarly to those reductions, compute recurrence relationships that are implemented across a loop. The importance of this is that those recurrence relationships can take the form of dependencies within the iterations of the loop, across the iterations of the loop, and would normally inhibit parallelization. But because they're very well structured, the compiler can actually exploit that structure to parallelize the loop despite the apparent dependencies across the iterations. We've also made many significant extensions to OpenMP's device support. We've updated the memory model, for example, to allow better control over when operations that occur on one device are visible on another device. One of the biggest extensions we've added is the work distribute construct, which is actually only available in Fortran, and it allows much more intuitive parallelization of array syntax in Fortran that is executed on a device in a target region. Another large set of additions adds several loop transforming directives, including the split directive and a couple other loop transforming directives. These actually implement sequential loop transformations. They have been included in OpenMP because OpenMP parallelization can sometimes appear to inhibit the use of those transformations automatically by the compiler. By including them in OpenMP, you can be assured that if you specify them on your loops, that they will be that the transformations will be applied to those loops, and then you can actually apply OpenMP parallelization to it, to the resulting transformed loop. The use of the term apply is consistent with the addition specifically for loop transforming directives of the apply clause, which now allows us to apply additional transformations to transformed loops, and in fact allows us to apply OpenMP parallelization constructs to the transformed loops when the resulting transformation, when the results of the transformation are such that you're assured that the resulting loop has canonical loop form and therefore should be able to be parallelized under the OpenMP loop parallelizing work sharing and such constructs. So the work sharing loop and the SIMD loop construct, and also the distribute construct that is used in target regions, the parallelized loops on other devices. A big change is that we've changed how we specify the supported compound constructs. They're now defined based on a grammar. Previously, the compound constructs were defined basically individually and somewhat haphazardly, to be honest. They were defined, somebody said, oh, it would be really useful if I could specify this directive and this other directive as a single directive. Now, basically, for the most part, if you can specify one construct nested inside another, you can specify it as a compound, the pair specified as a compound construct. All of the existing combined and composite directives are still valid, but now the set that you can use is much larger. This adds several constructs that had been requested. For example, target loop is now a valid compound construct. As I will end this talk, we've made several significant improvements to the usability and correctness of the specification by the way we actually implement the specification. And I'll cover some of that because they actually have significant benefits that we expect to realize as we go forward with future versions of the specification. So to illustrate one of the significant new features, I like to use a simple example. And in this example, it's a very short program. Assume it's in main. I've omitted the initialization of the array A because it just basically, the arrays A and B, because it would take up a lot more space to specify how we get the initial values for those arrays. We then encounter a loop that gives us basically the product, the inner product of these arrays scaled by some scalar S. All right, and that is captured inside of the task loop construct with a specified grain size. And so the question is, what is the effect of this code? Well, before 6.0, the effect is essentially that the iterations of the construct are executed in basically an arbitrary order by the specification that could be executed is essentially any order but in chunks of the size of iterations of number of 4,096 iterations. So the problem is that we haven't introduced any parallelism into the code at this point. And prior to 6.0, you basically had to include, first have a parallel mask construct around that code that would ensure that there were multiple threads available to execute the iterations. All right, so you would generate the tasks in the task loop just once for all of the threads inside of the inside of the primary thread of that parallel team. Right, and then all of the threads in the team are available to execute the tasks being generated by the task loop construct. So then you get the parallelization you would expect. Frankly, this is rather cumbersome in such a simple code to have to specify that you actually want to have parallelism available when, one would intuitively think that there were already threads available to execute those tasks. So in 6.0, we define the set of OpenMP as members of a logical thread, the set of OpenMP threads as members of a logical thread pool. Those logical threads then map to native threads, however the implementation chooses. All right, but the pool size can actually be specified by the OMP thread limit environment variable. Otherwise, it's an implementation defined number of threads that constitute that pool of threads. All right. Then we added this concept of free agent threads. So now you no longer need the parallel max directive in order to get parallelism in that task loop region. Instead, the full set, if you say, use the thread set clause on the task loop construct to say that it should be executed by all of the threads that are available in the OMP thread pool, then those other threads may actually pick up and execute the tasks that get generated by the task loop construct. The way this works is in order to properly support the existing applications, existing code, we created also a concept of structured threads versus unstructured threads. So the structured threads are those that are assigned through a parallel region to a team that's executing a parallel region. So in this case, the only thread that's assigned to a parallel region is the initial thread that's executing the entire program. And so then all of the other threads in the pool are available to execute those tasks as well as that initial thread. If you use the thread set construct within a parallel region, an explicit parallel region, then the threads in that parallel region are available, and any threads that aren't assigned to some other team are also available to execute. All right, so now you can get parallelism in your with your tasking constructs without having to explicitly create a parallel region. Makes the tasking support in OpenMP a lot simpler to use. It has some additional complexity, but the fact that we actually created this division between structured threads and unstructured threads significantly reduces the complexity in the implementation as well. Anyway, there are a number of other clauses and constructs and OpenMP runtime routines that support this concept of structured threads versus unstructured threads, some additional environment variables, and I encourage you to go and look at the OpenMP 6.0 examples document and look at the part on free agent threads in that document. That document was also already released earlier this month. So this is actually the first time that the examples document has been released at the same time as the new version of the specification. I've warned the chairs of the OpenMP examples subcommittee that the reward for good work is increased expectations, and that users will expect them to always release examples at the same time we release a new version of the specification. But anyway, that's out there, and you can go and see more about how to use free agent threads in that document. So the OpenMP tasking support is actually a very rich part of the specification that is not as well known as its device constructs or its traditional loop-based parallelism support. Nonetheless, there are some constraints in using OpenMP tasking. In particular, the dependencies provide simple and effective and efficient point-to-point synchronization. However, that point-to-point synchronization prior to OpenMP 6.0, so in versions 5.2 and earlier, the dependencies can only be specified between what we call sibling tasks. So tasks for which their task generating construct is encountered by the same task, right? So here I give a very simple example of performing an operation that is very well structured, so that in successive calls to this function, myfunc, they are operating on the same portions of the array that's passed in. All right. Now, if you pass in the same array, you should actually be able to execute tasks from different calls to myfunc concurrently, because you're guaranteed through the dependencies that they're going to be ordered across separate calls by those dependencies. However, as I said, prior to 5.2, those separate calls would have to be made by the same task. Otherwise, the dependencies do not apply across, to synchronize across different calling tasks. All right. The reason for this is that by limiting the dependencies to sibling tasks, we're able to ensure that you won't create a deadlock through those dependencies. You don't really need to do anything other than specify the dependencies. So you can alleviate this restriction, though, that the dependencies only enforce synchronization across that generating task, the encountering task. But that in that way you can allow concurrency across different encountering tasks. But that's pretty complicated. You really would like the dependencies to be able to specify that across different tasks that encounter myfunc, that they will then enforce the synchronization required. So in OpenMP 6.0, we had a new concept called transparent tasks, and these support significantly richer dependence graphs. So here I show a simple loop across that makes multiple calls to myfunc. All right, and by specifying that the tasks that are going to execute myfunc are transparent tasks, I guarantee that basically that the dependencies that are generated within myfunc are going to be honored across all of those different tasks. because each of those tasks is going to be a transparent task, which means that tasks, that dependencies from their parent task are now able to flow in, all right, to that transparent task. And in fact, if the subsequent tasks are dependent on the transparent task, then the dependencies from within the transparent task will flow out and into that following task, into that following dependent task. In this case, you can then use this concept recursively so that you can actually build a very rich dependence graph, basically all the way to the root of the first task that you're executing. All right. And so in this way, you can actually get the dependencies to be honored across a very rich dependence graph. All right. And nonetheless, we still are able to guarantee deadlock freedom. Again, this example is available in the examples document, and it explains at much more detail how the dependencies are going to be enforced and why they allow you to get the concurrency you want while still honoring the dependencies across the separate tasks that encounter the call to myfunc. All right. So we've made several other advances in the tasking model, and these all of these advances in the tasking model have pervasive impact. Some of the other major additions include adding support for dependencies and affinity of tasks generated by task loop directives. So now you can actually specify that the task loop directive. So in that example, I did not use the task loop directive on the loop inside of myfunc because I didn't want to go into how to specify dependencies on the tasks being generated by the task loop. And this is, but the actual support is through a new construct, a new subsidiary construct of the task loop directive called the task iteration directive. And this allows you to specify that depend clauses that apply to those tasks and also affinity relationships for those tasks. In addition, we have added a new directive called the task graph directive that allows you to essentially memorize a set of tasks that are going to be used with the same dependence relationships and the same task generating relationship across multiple times that you encounter those sets of directives. And this allows for the generation of those tasks be optimized significantly. This is particularly useful for device constructs. If you were not aware that the device constructs, such as the target construct, are actually task generating constructs. So now you can generate the target tasks, memorize the relationship between the relationships between the target tasks, and then generate them again, allowing all of those tasks to be kind of potentially merged into one larger kernel. And so that's where we get a big change in the specification. Most of the device constructs, including the target and target update directives, and in fact, the target enter data and target exit data directives, were already task generating constructs. As I mentioned earlier, target data is now a sequence of three dependent tasks. So it starts with a target enter data construct that is then followed by a transparent task and then finally ends with a target exit data construct. And these three have internal dependencies managed by the implementation that orders those three tasks, but otherwise does not inhibit the execution of them. So now you can say, pick up that block of three dependent tasks and execute it asynchronously. All right. We also added that the target data construct is a task group region by default. Potentially this reduces some of the concurrency that you might have had previously, but from our observation of many uses of target data, most applications were already assuming that target data in fact formed a task group region. Now, if you want to omit the task group region, you actually have to specify the no group clause on target data. Anyway, so that way you can again get the greater concurrency that was present previously. Otherwise, when you get to the end of a task group region, you're guaranteed that the the data mapping clauses will complete prior to the completion of the target data region. We are actually expecting in the future that other tasks, other constructs that are composed of implicit tasks, such as parallel and teams, will also build on the transparent task concept. And while we didn't actually adopt that specification in 6.0, we expect that in future we'll enable things such as being able to apply no weight to the parallel construct, and again allowing you to execute that, pick up those implicit tasks and execute them asynchronously. And that will be something that will definitely be added, if we expect, no later than OpenMP 7.0, but probably in 6.1. So, you know, in a couple years, the specification will actually support this asynchronous execution of parallel constructs. So as we look inside the implementation of the 6.0 specification, one of the big changes, well, so first of all, I want to state that I still consider the specification to be a document for OpenMP implementers. If you are a user and you want to get more insight into the changes in the 6.0 specification, then you should go really start with the examples document. You can look into the specification, but some aspects of the specification are structured in the way they are because we feel it's the best way to support implementers. Nonetheless, one of the things that we've done that we feel supports both users and implementers better is we significantly expanded the glossary in the specification. And we've changed how glossary terms are used. But previously, they were just used as plain text in the specification. Now the uses of glossary terms are actually encoded such that they are hyperlinked back to the actual glossary term. And the glossary actually has hyperlinks in the PDF version to all of the uses, all of the pages that include uses of that term. We've tried to be very thorough in encoding those uses. We may have missed a few, but the vast majority of uses of glossary terms now link back to the glossary. One of the reasons that this is a significant improvement for the specification, it means that those glossary terms have consistent spelling and usage throughout the document, and it greatly improves the consistency with which we use those terms. So hopefully this will benefit implementers and users alike as they look at the specification. Another thing we've done is in 5.2, we began moving the specification so that large portions of it are captured in JSON files, effectively a database that captures key aspects of the specification. In 5.2, all of the constructs, all of the directives, and all of the clauses were captured in JSON files. In 6.0, we've now captured all of the runtime routines and all of the aspects, all of the for the tool specifications for the OMPD interface and the OMPT interface, all of their callbacks, all of their routines, all of their entry points, basically all of the aspects of those interfaces are also captured in these JSON files. And in fact, in 6.0, the prototypes of the routines and entry points and such are actually generated from the JSON files. The reason that this, first of all, significantly improves the specification is that now you're guaranteed that everywhere we use the name of a routine or an entry point or such, that it's linked to that JSON file, that basically it has exactly the same spelling, so there can be no confusion between that spelling. We've also added all of the OpenMP types, all the OMPD types, and all the OMPT types. Those are now also captured in the OpenMP specification database. And again, that means that everything is significantly more consistent, and that the occurrence of typos is much less frequent. Another big benefit is that when you encounter it in the text, such as the encountering of the reverse construct here, it actually links back to the section that details that feature. So here it's a kind of trivial link from the use of the reverse construct in the semantics of the reverse construct section back to its own section. But throughout the specification, you can now, when you encounter the use of a OpenMP type, construct, clause, modifier, routine, entry point, what have you, you now actually get a link to the section of the specification that details that aspect of the specification. So we think that the specification is a lot easier to use now, particularly for implementers, but perhaps even users will find it easier to navigate. Nonetheless, these changes actually presage further changes in the future. Ultimately, our goal with the future changes is to support faster implementation of new versions of the specification. So by 7.0 and perhaps even by 6.1, we will have a version, a grammar in C and C++, and hopefully even in Fortran. Fortran experts tell me that there's difficulties with generating Fortran grammars. I'm not clear on the difficulties personally, but that will then support automated generation of the front end for the OpenMP specification and linkage to aspects of its underlying, of the implementation of the underlying features. Ultimately, we hope that by the time we are done with all of these improvements, that when we release a new version of the specification, that we can basically release a reference implementation of the new version. Now, it's quite likely that that reference implementation will not realize all of the performance that is possible given the new features, but we are hopeful that rather than being a multiple years effort to implement a major new version of the specification, that within 6 months to a year, we can have actually fairly high quality implementations of new versions of the specification. That's our hope. Hopefully, implementers will be able to realize the benefits that we think we'll be able to provide as we continue down this path of using a database to specify large portions of OpenMP. And with that, I'm happy to end this talk. And if you have questions, look for me or other members of the language committee. Hopefully they can answer any questions you have about OpenMP 6.0 and the future directions that we'll be pursuing.